all, respected Rajesh sir, respected Vivekananda sir, respected Himant sir, respected Saman sir. So today I am Gokul Mahanti. Today's my topic is quantum computing, guided by Dr. Vivekananda Naik. These are my development introduction, then roadmap to quantum computing, then quantum computer classical model, then hardware of quantum computer, qubits, then quantum gates and Gauss sphere, then quantum circuit, and then how to program in a real quantum computer, and then application of quantum computer, then error correction in the future of quantum computer, and then conclusion. So, in introduction, the quantum computers are the machines that use the properties of quantum physics to store the data and perform computation. And David Dutch is the father of quantum computing. And then this is the roadmap of quantum computer. As all you know, the Planck did quantization in 1900, and then EPR paradox in 1935, which is Einstein-Podolsky-Rosen paradox, where you have to counter quantum mechanics, and then all the then Feynman's and Weyl inequality and all the theory developed until 2007 in quantum computer. And then finally the software patent made in 2007, then goes on, and further development is going on in this field. Then quantum computer versus classical computer, and why we need quantum computer. This is the main fact, and there are very real world problem which cannot be solvable by our biggest classical computer. The complexity of the program is basically depend upon the time and how much amount of its memory can be consumed. Similarly, here we can see that there is a large number of functions are there. Blue mark is for n factorial. The graph is shown here, and red mark is for 2 to the power n, and blue mark for n to the power 2. And similarly, different mark are given for different functions, and we can see that the complexity is given here. The operations, or how much time or memory can take, and the elements means how much input we given. We can see that in n factorial and 2 to the power n, the graph is going steeper, means that it takes too much time or too much memory, but in other case it takes lesser time. This graph is for complexity, and so we can solve a large number of functions in classical computer, but for n factorial and 2 to the power n, we can solve it in classical computers. So here in previous slide, there is also n factorial, and here is also the n factorial graph is for lower input case. The classical computer is very much good. The program which take exponential rate of time or space cannot be solved by today's computer, but quantum computer can do. And the classical computer still have good result at a low input case. So we can see here that classical computer can give good result in blue mark, and the red mark is overshooting the blue mark in low input case, but in high input case the red mark is lower. So quantum computer is very much beneficial in large input case. Then the hardware of quantum computers, and the main component that makes a quantum computer run is the quantum processor. There are different types of flavors of quantum processor. So basically in quantum computers we need a two-level systems. So whenever we make a two-level system, then we can imply it in quantum circuit. So there is photonic. Photonic means the light wave which we use, and if the light wave is propagating in z direction, then it can be polarized in xy plane. So there will be a tangential polarization, and there will be a normal polarization. So we get two-level system. Then we can make it in quantum circuit. So this is what happens in photonics. In spintronics, or you know, the spin of a particle is plus half and minus half. So we can use it in spintronics. And the ion graph is basically all about there is a electrode where we have to trap the charge and we have to give RF frequency to manipulate the charge and so that we have two states, higher state and lower state, and we further get two level system and we can solve it. And superconducting also the same fact is there. There is Josephson junction where we have to give the current in reverse bias or forward bias, whatever we give to control the bits, qubits. So that's how we get two states, ground state and a higher state, to which we can manipulate and further we can control the qubits. And just like and then we have qubits. We already talked about it. And classical computer use bits like 0 and 1. Similarly, quantum computers use 0 gate and 1 gate, where the 0 and 1 in classical computers are deterministic in nature, but in quantum computers they are probabilistic in nature. Then there is matrix form, and the physical meaning of qubits is a two-level system. And qubits may be represented by a pure state, 0 gate, and 1 gate, where 0 is the upper state and 1 is the lower state. You can see it, and any state can be represented by a linear combination of 0 state and 1 state, and where alpha beta are coefficient, and the probability of getting 0 state is alpha square and 1 is beta square. Similarly, this is the screenshot of my IBM ID, where the upper part is IBM Sarnoff there and IBM QE, IBM Brisbane, and similarly given which upper part is represented the city name where the IBM office is held, and their LBS processor is given, system status online, their LBS processor is given, processor equal R3 equal R3 and here equal R3 and equal. So all the processors in quantum circuit are basically based upon the name of a bad name. And then this is qubits, we already talked about it. Qubits 127, 127, 127, and we have 33, 27. There may be 1000 or 2000 given. That is a simulator. So in quantum volume means the maximum amount of quantum circuit that can be implemented with the computer. That is that represents quantum volume. There 127, 32. There 128, 128, and there is clocks is also there. Clocks term, and clocks means the cycle of cycle of quantum volume that can be placed for unit time. So basically, how much quantum volume are placed over one another for unit time. Here clocks is 1904 and this is 2.2k. It's represent how fast the processor is. These are the basic facts of circuit. And here is also IBM Mumbai and IBM Kalwa, IBM Narathi, but you can see there is a catch because here 27 qubits got 64 quantum volume, but we have 7 qubits get 32 quantum volume. So in previous also there is 27 qubit we get 1 to 8 quantum volume, but in here 27 qubits 27 qubits we get 64 quantum volume. So the quantum volume can be raised up by removing the error in the quantum circuit. By reducing the error, we can increase the quantum volume, and higher the quantum volume, higher the processor efficiency. And then quantum gates, and in classical computer, gates are given by some logical expression, and it obeys Boolean algebra. Similarly, quantum computers use quantum gates, and the NOT gate is equivalent quantum computing Pauli X gate, where the NOT gate is changes the state from 0 to 1. Similarly, Pauli X gate can changes the state 0 gate to 1 gate, which you can see later in one diagram. Okay, so then this is the linear combination X alpha 0 gate and beta 1 gate. When act on Pauli X gate, then it gives beta 0 gate and alpha 1 gate. It changes the bit, so it can flip the bit. Then similarly, Pauli Z gate can flip the phase, and similarly, Pauli Y gate also can change bit flip. It can change bit flips and phase flips. Then the gates are represented by matrices, and it obey linear algebra instead of Boolean algebra. In classical computer, the gates are irreversible, but in quantum computers the gates are reversible. Means if I get something output is there in classical computer, then I cannot know what are my inputs. If I don't know the gate, then also we cannot get the input. But in quantum computer, only we have to make the table of the Pauli X gate or whatever be the gate given here. Then the unitary is the quantum gates are unitary, obey unitary transformation. So we can get that dagger. So when we add the dagger on the output, then we get the input. So these are the reversible gate. Similarly, here we can see that there are large number of Q1, Q2, Qn number of inputs are given, and similarly we corresponding get the outputs. Here the box is some gates is given in the real hardware and sorry in real quantum circuit, and some other gates are here H0 gate means H means Hedman. It is an important gate in quantum computer, and where H0 gate which can changes the state to plus gate, and H1 gate which changes the state to minus gate. Plus gate means the positive x direction. Okay, H equals to 1 by the Hedman gate have some matrix representation. Here all terms are written in matrix. So 1 by root 2, 1 1, 1 minus 1. You can changes z basis to x basis. And similarly SH0 gate equals to plus I gate. Where H0 means our already written here. H0 means plus gate, and when it takes on plus gate means our x axis. When x axis S matrix act on x axis, then it changes to y axis. That plus I means as y axis. We see later in next slide. There is also CNOT gate similar to XOR gate, and there is also swap gate which we can swap 2 qubits, and Toffoli gate which is also control node. Then this is the Bloch sphere, where Bloch sphere is used to represent a qubit. We can represent q gate or any arbitrary quantum state, the linear combination of 0 gate and 1 gate, where 0 gate is represented in z axis of and 1 gate is represented in negative z axis, and then where we can write as alpha 0 gate plus beta 1 gate 2 gate equals to alpha equals to r1 I theta 1. We take it alpha equals to r1 e to the I theta 1, beta equals to r2 e to the I theta 2, where theta 2 equals to theta 1 plus theta phi. So we give a relationship between theta 1 and theta 2. So by writing in terms of this theta 1 and theta 2, it gives us the freedom to use the spherical polar coordinates and represent the state in any point in the Bloch sphere, where theta gives the dependency of the state to move in plus z axis and minus z axis, and phi gives the dependence to move the state in xy plane. And then so we have three parameters r1, theta 2. We can represent in spherical polar coordinates. Then q gate equals to, so we can write it as cos theta by 2 by doing some mathematics. We can get from this relation cos theta by 2 0 gate, and e plus e to the power I phi sin theta by 2 1 gate. So there is also same thing we written here in terms of psi, and so we can rotate the qubits at any point on the sphere. Here plus axis represent the positive x axis, and the negative sign represent the negative x axis. It is the positive x axis 0 gate plus 1 gate by root 2. Similarly, in backward direction there will be negative x axis, which is 0 gate minus 1 gate by root 2. Similarly, y axis 0 gate plus I 1 gate by root 2, and negative x axis 0 gate minus I 1 gate by root 2. This is very much similar in our quantum mechanics spin matrix, where we write S dagger S plus equals to Sx plus Isy, and similarly S minus equals to Sx minus Isy, where we get Sx by taking S plus plus S minus by 2. Similarly these things are made like plus and minus, and positive x axis, positive y axis, and then we have in matrix form plus equals to 1 by root 2 0 gate plus 1 gate. 0 gate we already know 1 by 1 0, and 1 gate means 0 1. So by adding and 1 by root 2 normalization factor and giving adding the matrix, we get 1 by root 2 1 by root 2. Similarly in minus we get this, and similarly plus I means y cap direction, and minus y negative x y axis direction, and plus I equals to 1 by root 2 0 k plus I bar k. And similarly by doing some mathematics we can get this matrix. And then quantum circuit, not all gates are available in quantum computer, which we talk about in Hadamard gate. Hadamard gate is very much important because all gates are not available in IBM quantum circuit. There is no X gate in quantum computer. You must need to understand the matrix to perform an operation. So Hadamard when act on X gate, then act on H, then we get Z gate. And similarly, Hadamard on Z gate, then H equals to X gate. Um, uh, so by doing matrix transformation, we can get H Z H equals to X gate. So we can do the we can use the X gate in our quantum circuit. So here how we can use there is Q1 state, Q2 state, and we use X gate. Then we get Q1 test, Q2 test. Similarly, here it is the C node gate. C node we already talked later. Control node, there is control node, there is a target and there will be a operator. That's how we use C node gate. And then how to program in a real quantum computer? There is two methods. First is the graphical interpolation method, and there is another Pythonic method where we must know some Python to use that. And in graphical interpolation method, there is no need of Python. You just use circuit composer. Many physicists and chemists use the circuit composer, and because it is it is easy to create your own circuit, and the large circuit are done by Pythonic way. This is the screenshot of my IBM ID, IBM Quantum Lab, where this is the Hadamard gate, and this is the S matrix and this is the Z matrix. This is the oracle which is used to measure the state, and here Q0 is given there, and C4 is the classical channel where we get the output result. And there are large number of Q0 are there. There may be Q1, Q2, similarly large number of there. Just click right click on the Q0, then you can delete or add more Q0, and all the Q0s are in the zero state, or you can change it into one state. Once you get zero state, then you can use the gate to convert it into one gate state we previously saw it. And then different types of gates are there, and when we use the Hadamard gate on Q0, then we already see it gives 1 by root 2 0 k plus 1 by root 2 1 k. So the probability is 50-50%. So in this is the graph which is shown by simulator, where it is 50% and not exactly 50%. The graph is given, and bar graph is given, and then this is the block sphere diagram. Q sphere, block sphere is for single qubit, but for large number of qubits we use Q sphere, where it may be 0 k, 0 0 double 0 k, it may be 0 0 0 2 0 k, here 1 1 1 k is given. And there is the quantum lab for Pythonic way. If I do something in circuit composer method, then that will be reflecting Pythonic way. If I do some Pythonic way, then that will be reflecting circuit composer. You need only one type of use in quantum circuit, quantum computing. Then you can do other type of things like Pythonic way. Then here it is Q1 and there is Q0. I told that previously that there are large number of Q1 can be there, and there will be classical gate C1, and here we use Hadamard gate. Then we use a oracle, and which targeted to the classical channel 1, classical channel 0, and gives the result. And we there will be a folder, and if we click on there, and then we will choose the which type of circuit you would like to choose. In previously we see some of the IBM Mumbai or IBM Kolkata. Whatever you want to choose, you can put it and then run the circuit and you get the result. Then put it and get the result in. There are sorts 1024 means 1024 times the circuit is wrong and we get the mitigation is overrated one and mitigation time means it shows the error and here we to get 00 state 0.496 is the probability and 01 state is 0.503 so it is it's not 50-50 condition because we run it in real hardware. So in real hardware there will be some noise and due to the noise there will be error and that makes not 50-50 condition. But in simulator if you run then you get 50-50 condition. Here we use two gates Q0 and Q1. That's why you get 00 state 01 state. That's fast. We don't act any type of gate in one state, so that's why first state is 0 and 0 is 2 and for other 0 1 we get. Then the application of quantum computer and the application is to drug discovery and chemistry. To simulate complex molecule is not possible by the classical computer as the number of states needed to keep track all its interaction grows exponentially. So drug discovery and chemistry in general is likely to be being a lot of benefits using simulation in quantum computers. And in healthcare and diagnostic to detect the cancer cells it is very much useful because in cancer cell the how to detect previously before affecting the cells by doing some probabilistic way to study the system and then we can get the result which cell will be affected. And similarly in fraud detection the basic idea is that quantum computer is very fast and it can solve in factorial way. Then that's why the fraud detection often involves finding the optimal balance between false positive and false negative. And quantum computer can solve optimization problems faster and more accurately than classical computer with the help of superposition and determinism. And similarly, in machine learning, also we can use quantum computers can be used to train more sophisticated machine learning models that can be identify correlation and anomalies in the financial data with higher accuracy. This can be helped in financial industry and in also weather forecasting. Also, we can use it by taking into account more variables and processing data faster. Quantum computer could allow for more detailed climate models, and there is many more application of quantum computers like batteries, better batteries, and cyber security, and many more. And there will be error correction in classical computer. Also, we do error correction where the bit can be flipped 1 to 0 or 0 to 1, vice versa. Similarly, T is the probability of a single bit to flip from one state to 0 state, and not going to 1 to 0 state is the probability 1 minus 6. Okay, then how the classical system deals with this noise, and the idea is to give 3 bits repetition code encoded 0, 0 if we give 0 code then we represent it in terms of 3 bits 000 and then similarly 1 can be represented 111. If a single bit error code to distinct 3 bit strings, if a single bit flip then it becomes 001 or 010 or 100. Similarly 111 can also 110 or 101 and 011. So by flipping only one digit, then error detection the decoder decides whether the noisy string correspond to 001 or 111 by parity checkers. So only one bit will flip and we can solve it by parity checker. There will be a possibility of getting 2 bit flip, but the probability of flipping 2 bit is less. So we neglect it. And similarly in quantum computer, 0 cat can be written as 000 and 1 cat can be written as 111. And we use CNOT gate, control NOT gate to detect the error. Then future of quantum computer in India, there will be a large scale in quantum computing. QNU Quantum Light is the first and only India company to in the quantum safe cryptography space. According to the startup, it uses quantum physics concept to encrypt keys instead of traditional ways. India's National Quantum Mission project aims to deliver intermediate scale quantum computers with 50 to 1000 physical qubits by 2031 and make India one of the leading nations in the development of quantum technology and application. So the basic idea is to make 50 to 1000 qubits in physical qubits by 2031, and then the conclusion nowadays this is going on the reduction of noise in quantum circuit so that we can increase the quantum value. We already talked about it, and then quantum computing is actually emerging technology which can solve any complex problems. There is a lot of scope in quantum computing. Very soon, all our laptops and computers are going to be replaced with quantum computers, where we can do all the office work, project, programs, or anything like we do in our today's computer without knowing first the hardware is or how all the command processed inside it.